Okay, so welcome to the Oxford Discrete Maths and Probability seminar. This week it's a great pleasure to have Maria Chudnovsky, who's going to talk on K-blocks and forbidden induced subgraphs.
All right, thank you very much for having me. I must say I haven't given an online talk for a while, so this is a little bit of a throwback. So I didn't post my slides on the website, but if you have questions, please ask. I think it's a small enough group. Just please ask. There's no one in particular I'm trying to get to. So if there's something you didn't understand or a definition you forgot, so it doesn't hurt anybody if I say it again. Okay, so and then the next thing is this is the different theorems here are joint work with different people, and I'll say who did what as I get there. Okay, so let's see. So graph theorists, I work on graphs, and my graphs always have vertices, vertex set V and edge set E, and I think a lot about the structure of graphs that you can define by forbidding an induced subgraph, which roughly means you forbid configurations under deleting vertices. Right? This is a slightly less common containment relation in graph theory. Usually people think about, so the first thing you think about is subgraphs, where you delete vertices and delete edges, but the containment I always think about, or almost always, is you're just allowed to delete vertices. So let me say this more precisely. H is an induced subgraph of G if the vertex set of H is a subset of the vertex set of G, but then once you decided on the vertex set, you're stuck. If the two vertices are adjacent in H, if and only if they were adjacent in G, you're not allowed to just get rid of edges. So here's an example. This is G. This is an induced subgraph of G, because to get this from that, you delete this middle vertex. But this is not an induced subgraph of G, because if you wanted to get this right-hand graph from G, what you would need to do is keep all the vertices, but somehow miraculously get rid of this edge and that edge, and that's not an allowed operation. Once you've committed to the set of vertices, you can't touch edges anymore. And just for terminology, family is hereditary if it's closed under this operation, and there's the operation of taking induced subgraphs. All right, so first let me advertise this containment relation a little bit. One of the most well-known hereditary families is a family of perfect graphs, and these are graphs that behave especially well under coloring. Kind of a natural question to ask. So when you try to color a graph, right, you have the chromatic number, which is how many colors you need, and then you have the clique number, which is how many pairwise adjacent vertices you have. And of course, the chromatic number is always at least the clique number. And then you could ask, when is this lower bound achieved, right? And somehow it's interesting, right? When can you do as well as possible with respect to coloring? So that's a nice question. When are the clique number and the chromatic number the same? But it turns out it becomes an even better question if you close it under taking induced subgraphs. If you say the clique number and the chromatic number are the same for G and for all its induced subgraphs, then suddenly there's some kind of examples that are there because of low connectivity disappear, and you only get the real good stuff. So a graph is perfect if for all its induced subgraphs, their behavior with respect to coloring is as wonderful as you can hope, namely the chromatic number and the clique number are the same. And so these graphs have many nice properties. For example, so they were introduced by Claude Berge in the 1960s. And when he first introduced them, he made two conjectures about them. One was that taking complements preserves perfection, which is kind of an amazing thing, right? If you just read the definition, it's has nothing to do with taking complements. Taking complements means you change all the adjacencies. Two vertices that are adjacent, you make them non-adjacent. Two vertices that are non-adjacent, you make them adjacent. And so, so the fact that this coloring property is preserved under taking complements is kind of a magical thing, and that was proved by Lovaas in 1972. But then another conjecture that Berge made that maybe explains why. I mean, that definitely explains why. This is being perfect is closed under taking complements, and that's called the strong perfect graph conjecture, which says a graph is perfect if and only if it doesn't contain certain induced subgraphs, right? So it characterizes all minimal imperfect subgraphs. It characterizes all minimal obstructions for being perfect. And it turns out that the subtractions are odd cycles of length at least 5 and complements of odd cycles of length at least 5. So then, of course, it's clear why being perfect is invariant undertaking complements. That's because the obstructions are invariant undertaking complements. So, right, if the things that are not it are something in its complement, then the things that are it are something in its complement. And this is called the strong perfect graph theorem, and that's a theorem of Neil Robertson, Paul Seymour, Robin Thomas, and myself. Much later, it was published in 2006. And so anyway, so now we understand something about perfect graphs. We understand what the minimal imperfect graphs are. We have the weak perfect graph theorem. I'll sort of make a little detour here from the actual thing I want to talk about. One interesting thing about perfect graphs is that algorithmically they're very nice. There are various problems that are NP-complete in general, but for perfect graphs you can do them. You can solve them in polynomial time. For example, finding the biggest clique in the graph, or finding the biggest stable set in the graph, or if you have weights on vertices, finding the heaviest clique in the graph. All these things are NP-complete for a general graph, but they're polynomial if you know the input is perfect. And in fact, you can even make it a little bit better. So another thing that we can do with perfect graphs is test in polynomial time if a graph is perfect. So then you can make this algorithm robust. You give me a graph, I test if it's perfect. If it is, I find the biggest clique in it or whatever you wanted me to do. If it's not perfect, then I say I can't do anything. The graph is not perfect. So anyway, so algorithmically they're very nice, and but there's something that we still don't know about, even algorithmically speaking. So the fact that you can compute the clique number in the perfect graph is the theorem of Groce, Lowas, and Shriver. And the way they do it, they restate the problem of finding the biggest or the heaviest clique as a semi-definite program, and then use the ellipsoid method and use methods from combinatorial optimization to solve the semi-definite problem. But it's a problem in graph theory. Right? It's not a problem in semi-definite programming to find the biggest clique in a graph. So what we're still missing is a combinatorial algorithm. It's an algorithm where an algorithm that you can describe in terms of the input graph. Now, look at this vertex, look at that edge, look at this set of vertices. It's right. We don't really have a good definition for what a combinatorial algorithm is, but on the other hand, probably like everybody understands more or less what I mean. Sophie Sperkel taught me that a combinatorial algorithm is one where you don't need to use division in its description. And I thought she was joking, but actually she read it in a book, as it turns out. So that's what we're looking for, an algorithm without division. Now, in order to prove the strong perfect graph theorem, what my co-authors and I had to do was understand a lot about the structure of perfect graphs, and prove almost a structure theorem for perfect graphs. Prove a theorem that says that every perfect graph, either we can describe it exactly or it breaks apart along a nice cut set. So you would think if you know so much about the structure, you should be able to run algorithms. But the answer is no. The answer is there's still something missing. So I like to advertise this problem. Find a combinatorial algorithm to find max clique and perfect graphs, because I think there's something beautiful and interesting that we haven't discovered yet. Okay, so that was perfect graphs. And again, the real point of this slide was to show you a nice hereditary family. So then one might optimistically ask, do all hereditary families have nice properties? And the answer is not at all. Now what properties are nice? Well, let's sort of build up from perfect graphs. So for perfect graphs, the clique number and the chromatic number are the same for all induced subgraphs. What if I ask even for something much weaker? Say the chromatic number is bounded above as a function of the clique number. A lot less, right? Not equality, but just bounded, bounded by function. And even that is false in general. It's false for triangle-free graphs, right? The family of triangle-free graphs is hereditary, and yet there are triangle-free graphs with arbitrarily large chromatic numbers. So then another question is, well, maybe if you look at a hereditary family which is not the family of all the class of all graphs, something good happens algorithmically. Maybe you can find, you can always compute omega. And the answer is no, you can't even do it for graphs with no stable set of size 3. It's NP-complete for graphs of stable set of size 3. So somehow this does not generalize to all hereditary families. There is one lovely conjecture that does say something about all hereditary families, and sort of in a way tells you that excluding an induced subgraph is serious business, because what it says is that graphs with a forbidden induced subgraph behave qualitatively differently from general graphs. And let me say what I mean, or what the conjecture means. So the conjecture says for every graph H, there's an epsilon, depends on H, so that if I look at a graph G that does not contain H as an induced subgraph, right? So G is not the most general graph, it's a kind of graph that does not contain H. Then G contains a surprisingly large clique or stable set. So omega of G is the biggest clique in G, alpha of G is the biggest stable set of G in G. And the conjecture is that this number, the maximum of the stable set size and clique size, is polynomial in the number of vertices. It's a number of vertices to some power. So now what's so special about why is it qualitatively significant? Well, in general graphs, this maximum is log the number of vertices, right? There are graphs where the biggest clique and the biggest stable set are log the number of vertices. And yet, as soon as something is excluded as an induced subgraph, the asymptotic behavior changes, right? It really becomes a completely different function. It becomes the number of vertices to some power. So that's a nice conjecture. It's open, and there's been a lot of progress on it recently, but I'm not going to talk about that. So anyway, so this was so far advertisement for hereditary families. And so now we're going to ask which hereditary families have nice properties. And there are many nice things you can ask about. I'm going to focus on structure and efficient algorithms. I'm going to completely ignore this. There's a lot of work and a lot of sort of knowledge on this. When is the chromatic number bounded as a function of the clique number, but I'm not going to talk about that. I'm not going to talk about progress on the Erich-Heiland conjecture either, but I'm just going to talk about structure and algorithms. Just one slice of it. Okay. All right. So what does it mean? What does it mean, nice structure? We understand what efficient algorithms are. That means polynomial time algorithms. But what do we mean when we say nice structure? And you can debate it. But there's one notion that has been used in graph theory many times before, and that's something that really pertains to both. And that's the notion of tree decompositions and tree weights. So I would say this slide is kind of for a niche audience, because if you've never seen a tree decomposition in your life, you probably will not understand what it is by reading this. And if you know what a tree decomposition is, then I don't need to show this slide at all. So this is mostly for people who knew and forgot. But also I try to give some intuition as to what it is that we're trying to do. So even if you're you're not ready to prove theorems about it, you will understand roughly what's going on. Okay. So I give you a graph, and I want to represent it by a tree. I want to somehow measure, is this graph simple like a tree or complicated like a graph with a lot of cycles, right? So that's kind of the question. And so first I'll tell you what it means, representing by a tree. So you have graph G, and then a tree decomposition is a pair T chi, where T is a tree. And what you do is you assign subsets of vertices of your graph G to nodes of the tree. In this slide, I'll make sure to call to say vertices of G and nodes of T, so that it's not confusing. So we have a tree T. To every node of T, we assign a set of vertices of G. And there's some rules, right? So what does it mean to represent G by T? So the first rule is every vertex of G needs to be in some bag. Oh yeah, I forgot to say. So when I look at one node of T and I see what's assigned to it, I call it the bag at that node. So the bag at V, chi of V, is the set of vertices of G that are assigned to that node. So the rules are every vertex of G needs to be in a bag. Every edge of G needs to be captured in a bag, right? So there's some connection between adjacencies in G and what's going on in T. And then the last rule is that if I look at a vertex of G and I look at all the bags where it appears, that has to be a subtree. That has to be a connected graph. I can't just say, I'm going to put this vertex, this vertex X, I'm going to put it here and I'm going to put it there. If I put it here and there, I also have to put it everywhere in the path of the tree between these two nodes. So, and that's what makes it a representation. Right? Okay, so let me do some examples. So first of all, so in the next two examples, the blue graph is G and the fuchsia graph is T. So here I have G. G is a tree itself, and I'm going to construct a tree decomposition of G using the same tree. So here's the same tree in fuchsia. And now what I need to say is what vertices of G go into which bag. And the way I'm going to do it, I'll designate a root for T. Here it is. I designated 3 as the root. Now for every vertex of T, there's a unique path to 3, right? From 1, I go 1, 2, 3. From 4, I go 4, 3. So for every node here, I'm going to look at it and its unique neighbor in its unique path to the root. And that's what I'm going to put in that bag. So 1, its unique neighbor in the path to the root is 2. So in the bag corresponding to 1, I'm going to put 1 and 2. 5, its path to the root is 5, 4, 3. So the unique neighbor of 5 and its unique path to the root is 4. So in the bag corresponding to 5, I'm going to put 4, 5. 3, he's already there by himself. So the bag for 3 is just 3. And what, you probably noticed that what we just did is took a general tree and constructed a tree decomposition for it using the same tree as a representation tree, and so that every bag has size at most 2. Okay, so that's what we just did. We constructed tree decompositions with bag of size 2 for every tree. Okay, so here's another graph. This is not a tree. So the way, think of constructing that. Ignore the vertex 1 for a second. So now you have a tree. Now, if you look here on the fuchsia side, and if you pretend that you can't see the number 1, you'll see a tree decomposition of this subgraph of this tree 2, 3, 4, 5. So now I need 2, 3, 4, 5, 6. Now I need to do something with 1. I need to include 1 in some bags, and I need to include the edge 1, 2 in a bag, and I need to include the edge 1, 6 in a bag. So to do that, what I need to do is add 1 to this bag and add 1 to that bag. But then I remember that I have this rule that if 1 is somewhere and somewhere, then 1 also has to be everywhere in the path between these 2 places. And for that reason, I have to add 1 here and I have to add 1 there. And so this is a tree decomposition of this graph with bags of size 3. And in fact, it's and if this were a longer cycle, you could do exactly the same thing. And it's significant that here I could use bags of size 2, but here I had to use bags of size 3. Because what the size of the bag measures is how close your graph is to being a tree. So it shouldn't be surprising that this is closer to being a tree than that. Okay, so now let's summarize all of this. So I give you a tree decomposition. Its width is the maximum size of a bag minus 1. And then the tree width of G is the width of the best tree decomposition you can find. So it's the minimum over all tree decompositions of the width of the decomposition. And we say G has small tree widths. We'll say that means G is close to being a tree. And there's some justification for saying that. And the last thing is the tree width of a tree is 1, right? That's what we just did here. We took this tree or any tree, we built its tree decomposition with bags of size at most 2, so width 1. And so tree decomposition of a tree, the tree width of a tree is 1. And it's a theorem that if you're not a tree, then your tree width is not 1. So we did the best we could here. Okay, so that was sort of introduction to tree decompositions. And what you should really remember is that it's some way to represent the graph as a tree, and the width measures the size of the width is the size of the bags, and the width measures how close you are to being a tree. Now, why do we care? Well, we care for various reasons. First of all, it turns out that it's a nice way to represent the structure of a graph. If you're familiar with the Graph Miner project, a lot of it is finding interesting 3D compositions of graphs and then trying to explain what the graphs looks like based on the fact that first you represented it by some tree with simpler bags. And then another thing that happens with 3D compositions is that you can, with good 3D compositions, nice 3D compositions, is that you can use them for algorithms. So if you have a graph and you have a 3D composition of bounded widths for it, and in fact, like if you're an algorithms person, the first thing you will ask is, if I know that the tree is bounded, can I find the 3D composition? Do you need to give it to me? So luckily, it's all the same. You can, if you know the tree is bounded, you can find it in linear time. It's not a problem. So if you have a graph with small tree widths, and you have a small width 3D composition for it, you can use it to design efficient algorithms for various problems that are in general NP-complete. For example, finding optimal coloring, finding max weight stable set. So again, set a stable, set of vertices stable if there's no edge with both ends in that set. And so let me maybe show you something, show you sort of very roughly how to do this. Get after that. So I'm going to do something on my board now. So you might want to slide the divider between me and the slides. So here's what you do. So here's a 3D composition. And remember, every bag has bounded size. And so now what I want to do is find the biggest stable set, or the heaviest stable set in the graph. So the idea will be, you look, well, so first of all, you look at leaves, and for each leaf, you record all the maximal stable sets. And that you can do because every leaf has bounded size, so it doesn't have too many subsets, doesn't have too many maximal stable sets. So next, I'm going to ask a question. For a maximal, or for a stable set here, I can say for a maximal stable set here, what's its best extension to this subgraph, to the subgraph induced by the union of the bags here and here and there? And it turns out what you do is you look at this stable set and you see how it extends this way. You look at this stable set, you see how it extends that way. You take the union, and that's the answer. The reason it works is because every edge between a vertex in this bag and vertex in that bag is captured in that bag. That's exactly what 3D decomposition does. Every edge between here and there is captured in their common name, in their common answer. Okay, so now what did I do? For every stable set here, I can record how it extends downwards. So now also do it here. Very good. Now do it here. For every maximal stable set here, record how it extends downwards. But now I solve the problem, because now downwards is a whole graph. So let's call dynamic programming, and that's something you can do. Why could we do it here? Because each bag has bounded size, and so you can look at all its subsets in constant time. Now notice, actually, all I needed to do is that I could look at all maximal stable sets in polynomial time. And what I used is that I could look at all subsets in constant time. So I needed a lot less than what I used. So people now started thinking about a new parameter, which is called tree independence number. And that's exactly that. How many maximal stable sets are, like you want a 3D composition with polar many stable sets, maximal stable sets in each bag. And one way to achieve this is to say the size of the stable set of each bag is bounded. So instead of bounding the size of the bag, you bound the size of the largest stable set there. And that's a very fun subject that I think a lot about now. So I wanted to tell you. Okay, but the traditional thing you do is just look at bounded size bags, and then you can look at everything you want in polynomial time, and so in constant time, and so you can do not just maximum weight stable set, but also coloring and all kinds of things. Okay, so the point of this slide was to explain that bounded tree-width is a good thing. And people thought a lot about bounded tree-widths, mostly, and it's known completely what are the minor obstructions for bounded tree-widths, what are the subgraph obstructions for bounded tree-widths. But in the last 20 or 25 years, the field of induced subgraphs started to develop, and so now in the last 7 years, people started asking what are the induced subgraph obstructions for bounded tree-widths. And so that's really what this talk is mostly about. Okay, so in order to be able to tell you what the obstructions are, we need to first get to know some graphs that have large tree-widths, right? That's where the abstractions will come from. So because tree-decompositions are a well-known thing, there are a lot of graphs known with large tree-widths. So let me list some for you. There's the big clique of size, the complete graph of size n has tree-widths n-1. The complete vector graph that has tree-widths complete vector graph k and n has tree-widths n. And that makes sense. It's a very dense graph, so they're far from being a tree, so you should expect them to have large tree-widths. But now here's a very sparse graph. It's actually a planar graph. This is called, so what I've drawn here is called a wall, and then you can subdivide edges, and then it's going to be called a subdivided wall. So that's even sparser, and still it has huge tree-widths. Its tree-widths is the number of rows or the number of columns. And it turns out actually for subgraphs, that's the only obstruction. If you don't contain a big one of this as a subgraph, then your tree-width is bound. So somehow for subgraphs, everything is nice. If I don't have a big one of this as a subgraph, I don't have a big clique as a subgraph either. So it all ties together nicely. For induced subgraphs, unfortunately, these are all incomparable things. And after you see this and you think a little bit more about induced subgraphs, you also realize that this is a minimal obstruction. This is a minimal family of graphs with large tree-widths. So now what is this? Well, you take this wall, you subdivide it, and then you take line graphs. You take the line graph. Now, another way to describe that is you look at every degree 3 vertex in the subdivided wall and you replace it by a triangle in the bottom picture. Okay, so now we have 4 important examples: big complete graphs, big complete vector graphs, subdivided walls, and line graphs of subdivided walls. This is sort of what we knew from the study of minors or of subgraphs. That's where it ended. Okay, so one could ask, maybe this is all you need for subgraphs. We got extra clever and noticed we need to include line graphs and we need to include these two, and maybe this is it. Maybe that's enough. If you forbid those as induced subgraphs, you get bounded tree-widths. Unfortunately, the answer to that is a resounding no. So Cintiari and Trotnion constructed an example, constructed a family of graphs that are even hole free. So a hole is an induced subgraph, a hole is an induced cycle, an even hole is an induced cycle of even length. So I wrote it here honestly. So no even holes, no complete graph on 4 vertices, and yet arbitrarily large tree-widths. Right, for every k, there is a graph in that family of tree-widths at least k. Now let's see what's that got to do with this. Well, so they don't have big cliques because they forbid k4. They don't have c4, so that's k22. Now this graph, if you look at it, what you'll see is that it contains configurations like this: 2 vertices and 3 paths between them, pairwise anti-complete. And that's called the theta, but the point about the theta is that 2 of these paths have the same parity, have lengths of the same parity, say this and that's an even hole. So if you don't have even holes, you don't have those, and there is similar argument that you don't have this. So they showed that this initial collection of proposed obstructions is not at all sufficient. There are other obstructions, right? And then they made a conjecture that maybe at least if you bound the degree, then then this list of obstructions is sufficient. By the way, I'm going to call, just one last look at this slide, I'm going to call these obstructions basic, or sometimes I'll call them T basic, where T is sort of how big the tree width is. Right, so KT, KTT, a T by T wall, and the length of the T by T wall are T basic obstructions. Okay, it will be written down later. But, okay, so they made a conjecture that if you bound, so first of all, they made a conjecture that at least for even whole free graphs, if you bound the degree, then the tree width is bounded. And that's true. That's a theorem of Tara Abrishami, Christina Boshkovich, and myself. For every even whole free graphs of max degree at most delta, the tree width is bounded as a function of delta. And we developed a method to prove that theorem that we call the central bag method, which basically says in order to know how big the tree width of this graph is, it's enough to look at that carefully chosen subgraph. And what that allows you to do is deal with graph classes that admit natural decompositions. This central bag is a bit of the graph where you've already done every decomposition you can think of. And I really like talking about this, but I promised myself I'm not going to do it today. I'm going to talk about something newer. So that's all I'm going to say about the central bag method, except that it's we're still proving theorems using this method. Okay, so anyway, so this is done. This was done in 2020. It was done in the subcubic case by this group. And this group also conjectured that actually, if you bound the max degree, then the basic obstructions, forbidding the basic obstructions is enough to get bounded tree widths. And that was proved by Korhonen in 2022. Different method, nothing to do with our proof here. Okay, so now we understand what happens for bounded degree. If you're just looking at graphs of bounded degree, then tree width obstructions are what we would expect from minors, meaning this case. So now we have to go further. We have to go beyond bounded degree, unbounded degree, and bounded tree widths. Okay, so we're still going to forbid the T basic obstructions, KT, KTT, the subdivided wall, and the subdivided T wall, and the subdivided and the length of the subdivided T wall. And now the question becomes, what else? So I'm going to say a graph is T clean if it doesn't contain any of those. And so now I need tree width obstructions in T clean graphs. Okay, so Lozhin and Razgon also thought about it from a slightly different angle. In 2021, they proved the theorem, or they published the theorem, that tells you what finite family of obstructions would work, right? If I forbid a finite family of induced subgraphs, what does it need to be in order to guarantee bounded tree widths? And they prove that it's if and only if this family contains a big clique, a big complete biptide graph, a graph, all of whose components is a subdivided claw, subdivided K13, and the line graph of such a graph. And this is very nice. So just notice this is somehow orthogonal to thinking about T clean graphs, because here the first thing we did was forbid an infinite family, or the third thing we did was forbid an infinite family, all subdivisions of the T wall, the T by T wall. And they're thinking about forbidding finite families. So somehow it's different. It's not the same question, but from a different angle. But okay, so but they had a really nice proof method, and what I'm going to show you is a 2023 proof idea of their 2021 paper. So somehow they started it, but then this is not what they said, but this is inspired by and in the spirit of what they said. One thing I should say, my talk is called K-blocks and something. Really, I'm not actually going to talk much about K-blocks. I'm going to talk about something that we call LM stones. But some people know what a K-block is, and nobody knows what a LM stone is because we invented them. But they're kind of a refinement of a K-block. So I thought I would put in the title something that people can understand, and then I'll confess. Okay, so an LM stone is a subgraph that's isomorphic to an L thick KM. So you start with a complete graph on M vertices, and you replace each edge by L parallel edges. And I now realize that this is not, so there's a word subdivision missing somewhere. So you take the KM, you replace every edge by L by L parallel edges, and then you take a subdivision. And that's what an LM stone is. So it's a subgraph, which is a subdivision of the complete graph on M vertices, where every edge is replaced by L parallel edges. So here's a picture. It's always better with pictures. So for example, this is a K2-4 stone. So it's a K4, and then I replaced every edge by 2 parallel edges, and then I subdivided. And what we so far mostly focused on is that LM stones are built from L bananas. So an L banana is 2 vertices and L pairwise disjoint paths between. Right? So between every 2 vertices in an LM stone, you have an L banana. Okay, so now we got the terminology down. So then it turns out that basically, if you want to study induced subgraph obstructions to tree widths in T-clean graphs, you can assume there's a KK stone. You can assume there's a huge stone. The reason for that, so I'll just say something quickly about it. So there's a theorem of independently Erden, Weissauer, and Grohe and Marx that basically tells you that if you don't have a KK stone, and not basically, it tells you that if you don't have a KK stone, then you have a tree decomposition where every bed is in some sense simple. In one sense, it's simple, maybe, so there are 2 things that can happen. One is it only has a few vertices of large degree. And another thing is, another way of being simple is it doesn't have a big complete minor. And tree width obstructions are induced subgraph tree width obstructions are known in the bounded degree case, and they're known in no big click minor case. And it turns out that starting with this tree decomposition where every bag is in a known case, you can do something to it, which I'm not going to explain, and get a bounded width tree decomposition for the whole graph. So if only you didn't have a KK stone, then it's done by previous results plus this theorem that tells that you can put them together in this nice tree decomposition. So now suddenly the question becomes, what induced subgraph does a KK stone contain, right? All we need to come up with is a full list of induced subgraphs that precludes you from having a KK stone. And there are tricks for that. People know what to do for that. You use Ramsey theory a lot. So that was, so remember I said I'm going to describe my version of their proof. So that's what they did. They understood that they're KK stones. And then to get, and that was sort of the deep part of their work. And then to get those graphs from KK stones, that's not very hard. That's pretty stunning. So they did that. Okay, so now what are we going to do? So we figured, we can do more Ramsey than they can. So we did. And we're able to prove this beautiful theorem, which I'm not going to explain to you, but what it says is if you have no T-basic obstructions and no member of the following 3 infinite families, which I'm not going to describe, then the tree width is bound. Now, this is not a theorem that anybody would care about, but here's a theorem that somebody would care about. So what if I ask, what one graph do I need to exclude from a T-clean graph to guarantee bounded tree width, right? So it's H-free and T-clean. For what H's can I bound the tree width? And that's something we can now answer. Turns out this H has to be a graph, each of whose components is a subdivided star, right? So remember they said, Lojan and Rascon said, infinite family, for finite family, it's KT, KTT, this and that. For us, remember, we already made our graph T-clean. So there's no this, there's no that, there's no subdivided wall, there's no line graph of the subdivided wall. And then as soon as you exclude any graph, each of whose components is a subdivided star, the tree width is bounded. And turns out if it's if and only if, because of 2 constructions that I'm going to show you very quickly here. So one construction is due to Davis and Pohota, actually. So what happened was Pohota found this construction and then started to work on different things, and nobody who cared about this talked to him for years. And then Davis found this construction, and then suddenly we met Pahuata and we noticed, or he noticed that he already invented this. So it's a graph with, it's just a bunch of paths and then a bunch of vertices, each with one neighbor in each of these paths. And that's a graph of large tree-widths, and it's not captured by anything I've shown you so far. And then this is another one which is called the Death Star. The Death Star, and let me not tell you what it is. So anyway, so that was right. So that's a theorem with this list of co-authors, and we can characterize which one graph you need to exclude from T-clean graphs to guarantee bounded tree-widths. Okay, so the next question is, what finite family can you exclude from a T-graph, a T-clean graph, to guarantee bounded tree-widths? Right? We're not ready to characterize everything yet, so we're taking small steps. And so it turns out, I mean, this is a very recent result. So we're finished writing the paper now. So you can describe, you can get an if and only if theorems for which finite families work. And I'm not, so again, that's with this group, Bogdan Aleku, slightly different group, Bogdan Aleku, Seper Hajbi, Sophie Sprokol, and myself. And so I'm not going to tell you the if and only if theorem, but I am going to tell you a nice corollary, or kind of an easy to state corollary. So the following family works. It's not if and only if, but at least the if part works. So you take a bunch of paths, and you take a vertex, and then for each of these paths, what this vertex does, one side of the, so it has a neighbor in the path, and then one side of the path is clean, doesn't have any neighbors here. And then on the other side of the path, you can have whatever neighbors you like. So let's just understand why what I just described to you is a finite family of graphs. So you decided on the path and you added a vertex, and you decided where the rightmost neighbor is. So that's one decision. But now there are finitely many things you're going to do. You're going to say, allow all possible neighbors here, and all possible neighbors here, and all possible neighbors here. And now you made finitely many graphs out of this one decision you made, right? So the fact that it's many graphs and not one graph is captured by this wiggly edges. But finitely many because it's finitely many paths, and this bit is only finite. This bit is bounded lengths. Okay, so the corollary is that if you forbid this family H, then so you have a T-clean graph and you don't contain any member of this family, then the tree-width is bounded. And let me say something about the proof. It's going to be no details, but I'm going to say something. Okay, so first of all, there is an important lemma that says, if you look at a graph with no big clique and no big complete backtick graph, and you have many bounded size subsets, so a lot of, so many is much bigger than the size of the complete graph you forbid, and the size of the complete backtick graph you forbid, and the size of these bounded size subsets, right? So much more than all of that. Then you can find quite a few of the subsets that are actually pairwise complete to each other. So you started with a huge number of subsets, and now you can find a decent number of them, many fewer, but a decent number, so that not only are they disjoint, but there are no edges between them. Now, why? So we don't know who proved this lemma. We all saw it in many different places in our lives. So I'm not going to say who proved this lemma. It's certainly not me. So now, why is that good? Well, for example, if I'm now trying, right, so I look at a big tree-width graph and I would like to find something like that in it, I actually don't need to worry about the edges between the different paths P1, P2 through Pm, because find something with many, many more paths, and now hit it with this lemma, and I'm going to get a bunch of these paths with pairwise no edges between them. So that's one, right? Like remember, these questions are well known when you don't say induced. So every time I can find a place where I don't need to worry about induced, I made a good step forward. So suddenly I don't need to worry about being induced between these paths. So then the next application of this lemma, right? So now remember, we can assume there's a huge KK stone, and another application of this lemma allows you to arrange that in a KK stone. I'm just going to draw a picture of a KK stone so you can point at it. So here is there's a K3-4 stone. And so the next thing I can arrange is that if I look at a bounded radius ball around each branch vertex, so here, on the bounded radius, I can arrange that all these things appear pairwise complete to each other. And roughly it's the same thing, right? It's many sets of bounded size. I can arrange that many of them are anti-complete. And then another sort of many applications of this lemma tell you that if I could find this where all paths are short, that's again a win. You can turn it into an induced thing like that, and then you can find anything you wanted. So in every stone, in every KK stone, I can arrange that what's right near the branch vertices pairwise complete to each other, and all the paths are very long. Okay. So here it is. Here's my KK stone with all the properties I just promised you. So now look at some vertex in it. Here it is. And suppose it has neighbors and lots of paths. Lots of paths of this stone. Well, that's good for me again. You can remember all I'm looking for is a thing like that. A vertex and many little paths in which it has neighbors. That's exactly what I got here. It's a vertex and many paths in which it has neighbors. So I can get what I need. So another property is no vertex has neighbors and many paths. Okay, so now I told you everything I know about this stone. And now it turns out that if you forget the branch vertices, the tree is still big, right? This is a subdivision of, this contains a big clique minor. If I deleted the branch vertices, that big clique minor disappeared. But turns out it only disappeared from sight. In fact, there's another one in there. That's something you can prove, that even if you forget the branch vertices, there's still, that still contains a big complete minor. And so it contains, we can assume it contains another stone, smaller one, a K prime stone, but still pretty big. And so now what we're going to do is ask, how does the stone, the K prime stone that I get after I delete the branch vertices, how does it fit in to this thing about which I know so much now? For example, I know that no vertex has neighbors and many paths. So this is meant to be a picture of that. So the gray thing is the KK stone, cleaned up KK stone I started with. Now, here is a branch vertex of the new stone. So this guy starts many orange paths. And I know they're not kind of spread all over the gray stone because he doesn't have neighbors on many parts of the gray stone. So the way they all start roughly in the same place. They all start in this one path of the gray stone. And in fact, you can prove that they all start pretty close together to each other. And so then what you do is, I'm not going to explain how, but what you do is you say, so look at the many orange paths. Right here they all are. This is one, it starts and it continues. And here's another one, it starts and it continues. And then try to take a bit of such orange path and then a bit of the gray path on which it started. And that looks pretty good, right? So this is going to be my path. So this is going to be my X, right? So I'm looking for this. So the guy of high degree is going to be this. And then the path P1 through P2, through P1 through PM are going to be those that are going to consist half of an orange path where I know he doesn't have neighbors because he is the start of that orange path, and half of this gray path where I know he does have neighbors. And now the only thing you need to worry about is why is this plus that actually a path? And it's not if you just look anywhere, but if you have many of them, then some of them are paths. And that's enough what you need. And I'm going to stop here. Thank you very much.
So would anyone like to ask questions? I think we've a few enough people that you can just unmute and ask. Actually, I have one question, which is, yeah, thanks for a very nice talk. You've got several theorems that say if you're T-clean, then tree width is bounded. I mean, tree clean under various conditions, then true width is bounded. And you've got lots of applications of Ramsey in there, so I'm guessing the bounds are large. Is there a conjecture for what they should be? Should it be polynomial?
I don't think there's a conjecture. Certainly, I don't conjecture that. But yeah, I don't know. I think.
But there are no lower bounds that bump things up. Yeah.
I mean, right. There are some lower bounds, but I don't think we think that's the truth either. I'm not sure.
Other questions?
I mean, there's the grid theorem for subgraphs, but I don't think it's going to be the same for induced subgraphs. So
yep.
Anywhere near the same. So maybe since this don't seem to be the question, I'll say one other thing about that. So here, this is about bounded tree widths. There is another question: when do you get logarithmic tree widths? And that's also a nice question. Algorithmically, basically, there's no difference, or almost no difference between bounded and when the tree width is log the number of vertices. And there, you have to be honest. You can't just Ramsey. You can't just say, "Well, I'll solve the problem without saying induced," and now I'm going to throw all the Ramsey in the world onto it because because somehow the width, the size of everything you find is related to the size of the graph. It's not just a constant. And so I don't know. I mean, maybe from studying that, we'll understand a little bit better which Ramsey are needed and which Ramsey are just there to kind of make the proofs easier. That's just philosophy.
Thank you. Okay, so let's just all unmute and thank Maria again for a lovely talk.